Hello everyone, welcome back to Happy to Help Tutoring. Today we are going to discover one of the most beautiful relationships in mathematics, a relationship discovered more than 2300 years ago. So I've written these numbers 6, 28, 496 and 8128. So can you tell me what do these numbers have in common? Actually, they are called the perfect numbers. Now, what are perfect numbers? Perfect numbers are those numbers which are equal to the sum of their proper factors. For example, let me take an example of number 6. So, number 6. Now, what are the factors of 6? 1, 2, 3 and 6 itself. Okay, so leave 6. Apart from 6, all the 3 factors are called the proper factors, and if we will add them 1 plus 2 plus 3, they will be equal to 6. It means 6 is a perfect number, right? Similarly, if I take the example of 28, let us take the example of number 28. Now see, what are the factors of 28? It's 1, 2, then 4, then 7, then 14 and then 28. So leave 28. Rest all the numbers are its proper factors. Now if we'll add all these proper factors, 1 plus 2 plus 4 plus 7 plus 14, so they will sum up equal to 28. It means 28 is also a perfect number. So these are perfect numbers for you. Now let's understand what are Mersenne numbers. Okay, so what are Mersenne numbers? Any number in the form of 2 to the power n minus 1 is called a Mersenne number. Now what is this n? N can be any positive integer. Okay, so n can be any positive integer. So any number which fits into this formula is a Mersenne number. So let's understand it using our table. Okay, so I made a rough table. So we have to calculate 3 values. N can be any positive integer, 2 to the power n, and then we'll find 2 to the power n minus 1. So let's put n as 2. So 2 to the power n. So n is 2. It means it's 4. Then 3. N equals to 3. So 2 to the power 3, it is 8. Now n की value is 4. So 2 to the power 4, it is 16. Then let me put n equals to 5. So 2 to the power 5 is 32. Now 6. 2 to the power 6 is 64. Similarly, 2 to the, now we'll put n equal to 7. So 2 to the power 7 is equals to 128 and so on. Okay, now 2 to the power n minus 1. So we have already calculated 2 to the power n, which is 4 minus 1. So it will be 3. Similarly, 8 minus 1, it will be 7. 16 minus 1 is 15. 32 minus 1 is 31. 64 minus 1 is 63. And 128 minus 1 will be 127. So you can see all these numbers, they are the Mersenne numbers because they are following the pattern of 2 to the power n minus 1, where n is any positive integer, right? Now let's observe certain things. Now you can see out of these Mersenne numbers 3, 7, 31 and 127 are prime numbers. Now what are prime numbers? Which have only two factors, the number itself or 1. So you can see 3, 7, 31 and 127 are prime numbers. So see, the numbers, the prime numbers, okay, 3, 7, 31 and 127, they are called the Mersenne prime numbers. So these are our Mersenne prime numbers. Okay, so these numbers are called the Mersenne prime numbers because out of all these Mersenne numbers, only 3, 7, 31 and 127 are the prime numbers, therefore they are known as Mersenne prime numbers. Now again, let's observe something more. Now see, 3 is a Mersenne prime number and the corresponding value of n, that is 2. 2 is also a prime number. Now second Mersenne prime number is 7. You can see the corresponding value of n is 3 and 3 is also a prime number. Now 31. Check 31. 31 is a Mersenne prime number and the corresponding value of n is 5, which is also a prime number. Now see 127. 127 is a Mersenne prime number and the corresponding value of n is 7 and 7 is also a prime number. But see, it's not always true. Okay, these numbers 2, 3, 5 and 7 are prime numbers and the corresponding value is also a Mersenne prime number. Now you can see 15 is a Mersenne number but it is not a prime number, and you can see the corresponding value of n, it's 4, right? 15, the corresponding value of n is 4 and 4 is a composite number, right? Similarly you can see it's 63 and the corresponding value of n is 6 and 6 is also a composite number, right? But is it always true? Let's take another example. So let me take an example of n equals to 11. Okay, now see, if my n is 11, so what will be the value of 2 to the power 11? 2 to the power 11 is equal to 2048. Okay, so 2048 minus 1, it is equals to 2047. So see, 11 is a prime number, right? 11 is a prime number. So the corresponding 2 to the power n minus 1 should also be a Mersenne prime number. But see, 2 to the corresponding value is 2047 and 2047 is not a prime number. It's a composite number because it has more than two factors, like 23 into 89. So it has more than two factors apart from 1 and the number itself. It is also divisible by 23 and 89, therefore it is not a prime number. Okay, so it's an exceptional case. So let's understand it further. Around 300 BC, the Greek mathematician Euclid proved that whenever 2 to the power n minus 1 is a prime, it always gives a perfect number. Nearly 2000 years later, Leonhard Euler proved the reverse. He showed that every even perfect number must come from a Mersenne prime. Together, this result is called the Euclid-Euler Theorem. Now let's understand it better using a table. Okay, so let me write all the prime numbers and then Mersenne prime numbers, and then we'll try to figure out the relationship. So prime number is 2, then 3, then 5 and then 7. So we'll only take 4 examples. Now Mersenne prime numbers, 2 to the power 2 minus 1, which means 4 minus 1, it is equal to 3. Then 2 to the power 3 minus 1, it means 8 minus 1, that is 7. Then 2 to the power 5 minus 1, it means 32 minus 1, that is 31. Then 2 to the power 7 minus 1, it is 128 minus 1, which is equal to 127. So these are the Mersenne prime numbers. Let me highlight them: 3, 7, 31 and 127. Now let's calculate 2 to the power n minus 1. So 2, what is my n? N is 2 minus 1. It means 2 to the power 1, which is equal to 2. Now 2 to the power 3 minus 1, which means 2 to the power 2, which is equal to 4. Now 2 to the power 5 minus 1, which is equal to 2 to the power 4, and which is equal to 16. And then 2 to the power 7 minus 1, which is equal to 2 to the power 6, which is equal to 64. Now you can see a pattern. Let me highlight this also. Now you see, if I multiply this Mersenne prime number with 2 to the power n minus 1, okay, 1 power less than the prime number. So 3 2s are 6. Now we got our perfect number. 6 is a perfect number. Similarly, if I multiply 7 into 4, I get 28, and 28 is also a perfect number. Similarly, if I multiply 31 into 16, I get the third perfect number, that is 496. And the same way, if I multiply 127 with 64, I get 8128, which is also a perfect number. So can you see the pattern? When I multiply the Mersenne prime with a power less than n, we get a perfect number. So can I write a general formula? Okay, let me write it. So this is the general formula we got. This is Mersenne number. Now Mersenne number, when multiplied with 2 to the power n minus 1, we always get a perfect number. I hope it's clear. Let's see and observe more patterns. Okay, so let's start with number 1. Number 1. Now keep doubling it. 1, 2, then 4, then 8, then 16, then 32, then 64, and so on. Now see 1, we can write it as 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3, 2 to the power 4, 2 to the power 5, 2 to the power 6, and so on, right? Now you can check. If I add these two numbers, 1 plus 2, I got 3. Now 3 is a prime number, so let me multiply it by 2. So I get 3 into 2, I got 6, and see, 6 is a perfect number, right? Similarly, we can continue the series. So we got our first perfect number 6. Similarly, if we add the next number, that is 4, we get 4, 5, 6 plus 1, that is 7. Now 7 is again a prime number, so let me multiply it with 4. So 7 4s are 28. You see, 28 is also a perfect number, so let me write it here. Now let's continue the series. If I add 8 to it, so it's equal to 15, but see, 15 is not a prime number, so we'll not use it. We only want a prime number, right? So we'll add the next number, that is 16, and if we add this to this, it will come out to be 31, and 31 is also a prime number. If now we'll have to multiply 31 with 16, so we'll get 496, and 496 is the third perfect number. So similarly, we can write we can derive the perfect number using this pattern also. Okay, so let me write something more. Okay, so our first perfect number 6, I can write 6 as 1 plus 2, and then we multiplied it by 2, so 2 to the power 1. So I can write 6 as this, right? Then our second perfect number is 28. So see how I wrote 28. 28 is equals to the first 4 numbers sum, 1 plus 2 plus 4, and then we multiplied it by 4. So I can write 4 as 2 to the power 2. Am I right? Similarly, the next perfect number is 496. How I wrote 496? 496 equals to 1 plus 2 plus 4 plus 8 plus 16, and then we multiplied it by 16. So 16 is 2 to the power 4. Am I right? So we can write the perfect number in this format also. Now let's further move on. So let's see how the formula of Mersenne prime numbers is derived. So we started with 2 to the power 0, then 2 to the power, we'll add it, 2 to the power 1, then 2 to the power 2, 2 to the power 3, and so on until 2 to the power n minus 2 plus 2 to the power n minus 1, because we don't know where the n goes, so we'll keep it till here, and we don't know what is the sum of this, so let's assume that the sum of the series will be m. Okay, now what we will do, we'll multiply this whole equation. Okay, so this is my equation number 1, and now what I'll do, I'll multiply this whole equation with 2. Let's multiply it with 2. So let's do it. So when I'll multiply this whole equation with 2, what I will get? I will get 2 to the power 1 plus 2 to the power 2 plus 2 to the power 3, so on, 2 to the power n minus 1 plus 2 to the power n equals to 2m. Right? So this is my second equation. So this was my first equation and this is my second equation. So let's subtract, equation 2 and equation 1. So I am going to subtract equation number 1 from equation number 2. So let me write equation number 2 below. So equation number 1 is 2 to the power 0 plus 2 to the power 1, then 2 to the power 2, then 2 to the power 3 plus 2 to the power n minus 2 plus 2 to the power n minus 1 equals to m. Right? So we got this. This is my equation 1. Now I'll subtract it, and when I'll subtract it, you can see everything will get cancelled. See, everything will get cancelled. So everything will get cancelled. So in the end, what will left is 2 to the power n minus 1 will be left. 1 is 2 to the power 0. 2 to the power 0 is equal to 1. So in the end, what will left? 2 to the power n minus 1, which is equal to 2m minus m is m. So this is the formula from where we got the formula for the Mersenne prime numbers. I hope it's clear. So let me write something. So you remembered how we wrote these perfect numbers earlier? 1 plus 2 into 2 to the power 1. So I can write 1 plus 2. 2 plus 1 is 3. So I can write it as 2 to the power 2 minus 1 into 2 to the power 1. See, it is again exactly equal to 6. 2 to the power 2 is 4 minus 1, that is equal to 3. And you can check the relation. This is 1 and this is 2. So we are multiplying it with 1. So it is a prime number 2 and we are multiplying it with n minus 1. 2 minus 1 is 1. Similarly, 28. I can write 1 plus this number, this thing. I can write it as 2 to the power 3. Right? Minus 1. So 2 to the power 3 is 8. 8 minus 1 is 7 and the sum is also equal to 7, and we then multiply it with 2 to the power 2. So again you can see this is 3 and this is 3 minus 1, 2. Right? and then 496. 1 plus 2 plus 4 plus 8 plus 16, I can write it as 2 to the power 5 minus 1, because this is equal to, the sum of this is equal to 31, and 2 to the power 5 is 32 minus 1, that is 31, and then we'll multiply it with 2 to the power 4, and again you can see that if this is 5 and this is 1 less than 5, which is 4. So again we have proved that formula of perfect number, right? Let me write it again. So you can see from the 3 examples that 2 to the power, if it is n minus 1, and if I multiplied it by 2 to the power n minus 1, okay, 1 less than this number, 1, see, this is 1 less than this number is 1 less than 3, this number is 4 is 1 less than 5. So we can make a formula. This is 2 to the power n minus 1 Mersenne prime number, and if we multiply it with 1 less than the value of n, we will always get a perfect number. So yes, it's interesting. We got the relationship between Mersenne numbers and perfect numbers. I hope it's clear to you. There are still unsolved mysteries. Nobody knows whether infinitely many Mersenne primes exist or not. Nobody has found an odd perfect number till date. Every perfect number known today is even number. Every even perfect number comes from the Mersenne prime. See, mathematics is full of beautiful patterns. A simple formula, 2 to the power n minus 1, connects prime numbers, geometric series and perfect numbers in one elegant theorem. This is why number theory continues to fascinate mathematicians even after more than 2000 years. If you enjoyed this connection between the Mersenne prime and perfect numbers, don't forget to watch my previous lecture on perfect numbers, where we discussed the properties, examples, and how to check whether number is perfect or not. Thank you so much. Meet you soon in the next lecture. Keep learning.